Alrighty, I'm gonna fly through some slides at the beginning here in hopes that we can get to the key experiments that kind of demonstrated a violation of Bell's inequalities at the end. Because the first few slides were just kind of reviewing what we did at the end of last class, but in general terms. So every time we add a qubit to a quantum system to create a new one, the state space doubles. And that's because we multiply the dimension of the original system state space by 2 when we do the tensor product. So a 3-qubit quantum system has a state space of dimension 8, and an n-qubit quantum system state space has a dimension of 2 to the n. And so we can kind of write what we were doing last class in general terms, and we can say that the state space associated with our n-qubit quantum system has 2 to the n dimensions. And we can write it in the c to the 2 tensor n state space. And it's generated by the elementary tensor products of the 1-qubit quantum states, like is written here. And we say that that quantum state is separable if it can actually be written as an elementary state that's a tensor product of the individual qubit states. And otherwise, it's entangled. So we can kind of simplify this kind of long-winded notation using Ket notation. So if we are thinking about this kind of 8 state entangled system, we can just write it as 1, 1, 0, 1, 0, 1, 1, 1. Knowing we have 8 qubits, we could also write this as a possible state of the 256 states in our 8-qubit system. So 2 to the 8 is 256, and this represents one of those states, and it's just labeled with a base 10 number. So it's 215 of 256. And so the subscript on the outside of these types of base 10 numbered kets is just telling you how many qubits are in your system. So in the n-qubit kind of generalization, our kets are composed of only zeros and ones, and those are called the computational bases, just like before. So for our 3-qubit system, the computational bases are 0, 0, 0, 0, 0, 1, and all the permutations of zeros and ones in that 3-qubit system. But you can write that in sort of the base 10 notation, where you're labeling each of these states with a number. All right, so if when we use the digital form of the ket, we number the probability amplitudes or coefficients using a number inside the ket symbol. So if my quantum state is A0, 0n plus A1, 1n plus blah, 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 A2 to the A to the A2 to the n minus 1, 2 to the n minus 1, n, then we have the sum of the squares of the probability amplitudes equaling 1, just like before. And if we want to write a ket like this one, we can shorthand it as 0 tensor product n. And if for a given n, we let phi and psi be 2 computational basis kets, then the inner product of those 2 kets is 1 if they're identical, and it's 0 otherwise. And we saw that last time for the 2-qubit case. And if one of our quantum states has a 1 in the jth position and a 0 elsewhere, and the other quantum state has a 1 in the kth position and 0 elsewhere, then the outer product is just the n by n square matrix that has zeros everywhere except the j and k positions. So if we're talking about the outer product of 0 with itself, then it's the familiar 1, 0, 1, 0, 0, 0. And the outer product of 1 with 0 is 0, 0, 1, 0. And the outer product of 0 with itself plus the outer product of 1 with itself is the 2 by 2 identity matrix, like before. All right. And so we can come back, and once we think about these entangled states, we can think about the density matrix, and nothing has changed. So if we have our quantum state psi being a multi-qubit quantum state, an entangled state, its density matrix is defined in exactly the same way as we defined it before. And so if we have this multi-qubit quantum state defined as psi is A0, 0n plus A1, 1n, etc., then the density matrix is the outer product. So it's the vector times its adjoint, just like before. So nothing has changed with the density matrix. Okay, so let's talk about multi-qubit quantum gates. So a quantum gate operation that operates on one qubit, like we saw before, has a 2 by 2 unitary square matrix in a given basis. For 2 qubits, it's a 4 by 4 matrix. For 10 qubits, it's a 2 to the 10 by 2 to the n, 2 to the 10 matrix, which is like 1024 by 1024. Usually, when we're dealing with these quantum systems, we're not entangling that many qubits. We're usually entangling pairs of qubits, maybe 3. So let's look at some of the lower dimensional entangled gates, multi-qubit gates. So let's start by looking at what it means to apply a Hadamard gate to each qubit in a 2-qubit system. So we remember that the Hadamard gate looks like square root of 2 over 2 times 1, 1, 1, minus 1. And if we have the 2-qubit states defined as before, so we have our first qubit state with the subscripts 1 and our second qubit state with the subscripts 2, then if we want to apply the Hadamard gate to both, then we have to compute the tensor product of the Hadamard gate applied to qubit state 1 with the Hadamard gate applied to qubit state 2. And we can rewrite that in a really simple way. So we can do the tensor product of the Hadamard gates times the tensor product of the 2 quantum states. So we already know what the tensor product of the 2 quantum states looks like. We did that last class. And so now we just got to figure out what this guy looks like. Okay? So what does it look like? So if you think about the definition of H, so I'll rewrite it here. So it's the square root of 2 over 2 times 1, 1, 1, minus 1, or if you want to just keep the square root of 2 over 2's in, square root of 2 over 2. Think about using the technique that we've looked at for creating tensor products. What is the tensor product of H with itself? So all we need to do is multiply each element of the Hadamard matrix by a Hadamard matrix, right? So it's square root of 2 over 2 times the Hadamard matrix. So when we go ahead and do that out, when we multiply square root of 2 over 2 by square root of 2 over 2's, we get 1/2. So we're going to end up with a square matrix that looks like a bunch of 1/2 and minus 1/2. And then the one in the bottom right corner is going to be the opposite, right? So we have minus 1/2, minus 1/2, minus 1/2, 1/2. And so we can rewrite this in a much simpler way. We can call it square root of 2 over 2 times H, 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 minus H. So this matrix puts both of our qubits in a 2-qubit system that are each initially at 0 into superposition. So no problem. When we're dealing with 2 qubits, it doesn't get too hairy. And if we want to deal with 3, we do exactly the same thing. And what we realize, if we kind of do this recursively, that we can actually see that for an n-qubit quantum system, the multi-qubit gate for Hadamard is just square root of 2 over 2 times the n minus 1 2 by 2 matrix, composed matrix. So earlier, we saw that applying the Hadamard gate to a state 0 brought it to the equator. It turned it into a plus state. And so that tells us that the Hadamard gate brings us to square root of 2 over 2 times 0 plus 1. So that's a balanced superposition of 0 and 1. And so if we think about the 2-qubit Hadamard gate, so we have the 2-qubit Hadamard gate applied to our quantum state 0, 0, so both qubits initialized to 0. So that's just the tensor product of the Hadamard gate with itself times the tensor product of the 0 state with itself, which just gives us this nice form, 1/2 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And if we want to think about the 3-qubit system, so the kind of tensor 3 Hadamard gate applied to all of our 3 qubits initialized to 0, it's just going to be square root of 2 over 4 times all possible permutations of the 0s and 1s in our 8 qubit system. And the pattern continues, right? So this shows that applying the Hadamard gate to each qubit initialized to 0 creates a balanced superposition involving all the Ket basis vectors, just like we saw for the 1-qubit system. The number out front is there to ensure that the square of the absolute values of the square of the absolute value of the Kets is 1. This normalization constant, just to kind of generalize it for ourselves, it's 1 over square root of 2 to the n, right? Where n is the number of qubits. Okay, so I flew through that. Everybody following? Not too bad. All right, so let's kind of think about what we just discovered. So if we have 3 classical bits, then we can represent all of the possible permutations of those classical bits, but we can only represent them one at a time. So at any given time, if I have 3 bits, I can represent 0, 0, 0, or I can represent 1, 1, 0. But what's cool is that the 3-qubit state, the 3-tensor Hadamard gate applied to my 3-qubit state, everything initialized to 0, it contains each of the corresponding Ket basis forms at the same time. So it's a balanced superposition of all 8 possible permutations. So we can write it in the sort of base 10 notation here as follows. Okay, so just to summarize the Hadamard gate, for an n-qubit system, the Hadamard gate that we need to create, to take that n-qubit system into a balanced superposition is just the tensor n Hadamard gate, which you can write as square root of 2 over 2 times the 2 by 2 matrix that contains the n minus 1 tensor products of the Hadamard gates. And you can think about this form of the notation in a sort of summation type form as well. So if we think about an n-qubit register, so here a quantum register, we're just thinking about a collection of qubits that we were using for computation, and all qubits in our register are initialized to 0. So if our quantum state, we can write like the summation of a sub j times j sub n, where the sum of the squares of the coefficients is equal to 1. So it's just a little bit of a different notation. Then that allows us to more simply express the formula for the balanced superposition of n qubits. So if we have n qubits, then it's Hadamard Gate tensor n times our all of our qubits initialized to 0, and that's equal to 1 over square root of 2 to the n times the sum from j equals 0 to 2 to the n minus 1 of j sub n. So that's exactly what we wrote here in the 3-qubit system, for example. Just generalizing it. All right, so the probably most important quantum gate for entangled systems in quantum computing is the CNOT gate. It's used to create entangled qubits. And it's not the only kind of gate that can do that, but it's the simplest one, and it's super common to use it. The C in the CNOT gate stands for control. And unlike the 1-qubit X gate, which unconditionally flips 0 to 1 and vice versa, this control NOT gate has 2-qubit inputs and 2 outputs. And we remember that all of our quantum gates are unitary, they have to be reversible, and for that reason we have to have the same number of inputs as outputs. So let's call our qubits, our 2 qubits that we're going to entangle, Q1 and Q2, and their states are psi1 and psi2. So here's how the CNOT gate works. It takes our 2-qubit quantum states, psi1 and psi2, and if psi1 is 1, then the state of qubit 1 stays psi1, but psi2 becomes flipped, x times psi2. So otherwise, the states of Q1 and Q2 are not changed. So if I put this another way, the CNOT gate operates like an identity gate, so it does nothing for psi1, for qubit 1. And when psi1 is equal to 1, the CNOT gate acts as an X gate for psi2 for qubit 2. Otherwise, it acts as an identity gate. So that's why we call CNOT a conditional bit flip. Okay? It only flips the second qubit state if the condition is met. If the state of the first qubit is 1, that's the condition. All right, so here's what the matrix looks like. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. So this is a permutation matrix that swaps the third and fourth coefficients of our 2 qubit states. The upper left matrix here, right, this is just the identity matrix. And the lower right matrix here, if we are chopping this into 4 pieces, is just the X gate matrix. So sometimes when you're looking at these more complicated 2-qubit gates, it's helpful to chop them up into little 2x2 pieces and ask yourself what's happening. So I can summarize what the CNOT gate does for our standard 2-qubit bases. So if I apply CNOT to 0, 0, I get back 0, 0. If I apply CNOT to 0, 1, I get back 0, 1 because my condition is I only flip if my first qubit is 1. So if I apply CNOT to 1, 0, then I get 1, 1, flip the second qubit. And if I apply CNOT to 1, 1, then my condition is met and I flip the second qubit. All right, so we can combine the CNOT gate and the Hadamard gate, and we can do other stuff. So if I apply the Hadamard gate before and after the CNOT gate, it kind of illustrates an interesting property. So here's what I want to do. I want to develop some new matrix. I'm going to call it M, which is just kind of sequentially doing a Hadamard gate, a CNOT gate, and then a Hadamard gate. So I can reduce that matrix, or that operation, to a much simpler 4x4 matrix. What does this matrix do? I guess by inspection, well, maybe you can tell me. What does this matrix do, just by inspection? Maybe we can chop it up. So what it does, it swaps the second and fourth coefficients of our standard Ket expressions. So let's look at what it does. So if I apply M to 0, 0, then I get back 0, 0. And if I apply M to 0, 1, I get back 1, 1. And if I apply M to 1, 0, I get back 1, 0. And if I apply M to 1, 1, I get back 0, 1. So take a look at what happens to the second qubit. If it's 1, then the first qubit flips. And if it's 0, then it remains the same. So this is the opposite of the CNOT gate, and we call it the reverse CNOT gate. So M is generated by composing the Hadamard gate and the CNOT gate, and it makes this new operation that's the opposite of CNOT. Yeah, so with our CNOT gate, like we saw, our condition was if the first qubit is 1, then we flip, and here it's the opposite. Okay. So here's where I wanted to make sure we got today. And this is the experiments that show us entanglement. So this starts back in 1935. So Schrödinger wrote this paper. It was called The Discussion of Probability Relations Between Separated Systems. And he says that when two systems, of which we know the states by their respective representatives, enter into temporary physical interaction due to known forces between them, and after a time of mutual influence, the systems separate again, then they can no longer be described in the same way as before. So he's describing entanglement. And he says, I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. By the interaction of two representatives, by the interaction, the two representatives have become entangled. he kind of goes on and talks about what separable means, and he says that a pure quantum state is entangled means that it's not separable, and for the simplest case of two distinct spinless particles moving on a line, being separable means that the wave function can be written as a composition of the two wave functions. The wave function of the composite system can be separated into the individual components. So what prompted Schrödinger to call entanglement the characteristic trait of quantum mechanics was a paper published in 1935 by Einstein, Podolsky, and Rosen, thinking about an EPR experiment. So that seminal paper described the seemingly paradoxical consequences of entanglement between two particles that are so distant that any interaction between them can be completely ignored. So let's look at, this was a thought experiment, it was not a physical experiment, okay? But let's look at what the thought experiment was. So in this experiment, we have pairs of entangled particles prepared in a singlet spin state. So y'all remember what a singlet spin state looks like, right? Spins paired. And you're going to send a member of each pair to Alice and to Bob. The spin direction of each particle is, in the initial state, totally undetermined. And at some distance from that source, labeled S in the picture, one particle from each pair passes a measuring device that's operated by Alice that measures the spin component in the z direction. That's what's shown in the blue arrow here. After passing Alice's measuring apparatus, the particle appears with a quantized spin in the z direction with either spin up, which is what's shown in the figure, or spin down. And due to this strict anti-correlation between the spin orientation of the particles in the starting singlet, at the same time as Alice measures her particle with spin up in the z direction, then Bob's particle has to appear with spin down in the z direction. Okay. So in this way, the measurement performed by Alice effectively acts as a measurement of the other particle. Okay, so the EPR paradox that is described by Einstein, Podolsky, and Rosen appears if Bob instead chooses to measure his spin of his particle in the x direction. So that's what's shown by the red arrows. So instead of measuring it in z, he measures it in x, but Alice measured hers in z. So when that happens, Bob's measurement has a 50-50 chance of giving spin up or spin down. And that's a contradiction, right? Because these spins are started off as a singlet and they have to be strictly anti-correlated. And the reason this happens is that spin in z and spin in x or y, they're incompatible, non-commuting observables like position and momentum. We can know the spin along only one axis at a time. And so a spin up particle in z has undefined spin in x and y. Okay, so that's kind of the original paradox that was presented in this classic paper. So in 30 years later, basically, John Bell came in and published a paper called On the Einstein-Podolsky-Rosen Paradox. And he showed mathematically that no so-called hidden variable theory would be able to reproduce all the results of quantum mechanics. He showed that all attempts to construct what he called a local realist model of quantum phenomena are doomed to fail. And in his explanation, local is related to the impossibility of instantaneous signaling, so you're limited by the speed of light. And realist means the outcome of any experiment is fully determined by the properties of the system that exist, and they're independent of any measurement, because that's how things are in reality. We can sort of generalize the ideas that Bell wrote down in his 1964 paper into like a category of things called Bell-like theorems. So what Bell did in that 1964 paper is he first derived an inequality for a certain correlation function that has to be obeyed using his local realist theory. And he then showed that for some experimental conditions, the predictions of quantum mechanics violate that inequality. And the thought experiment that he considered isn't really conducive to like building an experiment to test, because it makes assumptions about the detectors that can't be justified in real equipment. And so it took a long time later for people to come around and to think about how to demonstrate what Bell proposed. So, we can't exactly prove what Bell laid out, but we can kind of design a slightly different system. So here's the layout. So we have Alice and Bob, and they're in very separate locations. And Victor comes in, he prepares a pair of particles and sends one to Alice and one to Bob. Alice gets her particle, she chooses to perform one of two possible measurements. Maybe she flips a coin to decide which one. And she denotes these measurements by A0 and A1. And both A0 and A1 are binary measurements. So the result of A0 is either plus or minus 1, and the result of A1 is also either plus or minus 1. And when Bob receives his particle, he chooses one of the two measurements, B0 and B1, again, which are both binary. So simple setup. All right, so now we're going to suppose that each measurement tells us something about the property of the particle, like its spin or its polarization state or whatever. So if Alice chooses to measure A0 and gets the result plus 1, then the particle she received carried the property plus 1 for a property, so a value plus 1 for a property A0. So if we think about a combination of measurement outcomes from Alice and Bob, so like this combination here, because both A0 and A1 take the values plus or minus 1, then either A0 equals A1 or A0 equals minus A1. And in the first case, the right-hand side of the expression up there, A0 minus A1 times B1, that has to equal 0. And in the latter case, where A0 equals minus A1, then A0 plus A1 times B0 has to equal 0. So one of the terms in this expression goes to 0, and the other one goes to plus or minus 2. So if you repeat this experiment lots of times, the average value that you get from the combination A0 B0 plus A0 B1 plus A1 B0 minus A1 B1 across all the trials must be less than or equal to 2, right? We can agree on that based on what we just said, right? Choices are either you get 0 or you get 2. So if I do the measurement a bunch of times, then I'll get 0 or 2 a bunch of times, and so the average needs to be less than or equal to t. All right, so this thing is the Bell inequality. It's an example of a Bell inequality. This one is specifically called the Clausen-Shimoni-Holt inequality. It's the CHSH inequality. Bunch of people's names. And its derivation that we kind of just walked through depends on two assumptions. First, that the underlying physical properties of A0, A1, B0, and B1 exist. Fair? Independently of being measured, that is. So that's the realism assumption. And then the second is that Alice's choice of action can't influence what Bob's result is, and vice versa. And that's the locality assumption. So the assumptions are realism and locality. So same thing that we talked about in the last slide. All right, so then the big question is, how do you actually design an experiment to test this? What system should you use? And so that's where John Clauser came in. And he thought that the photoemission in calcium might work in this to do this test. So here's an energy level diagram for the different states of calcium. And in this experiment, here's your ground state. I'm going to excite using 227 nanometer light. And that excitation results in the generation of two photons. One of those photons has a wavelength of 551 nanometers, and one of those photons has an energy of 422 nanometers, and they have the same origin, and they kind of emerge in a cascade. So the experimental design is shown here. We have Alice and Bob. We have our source that's generating these two photons. And we're going to send each of them in opposite directions. And Alice and Bob both have two-channel polarizers. It's just a polarizer, light polarizer, like we've talked about before. Yeah, just up or down or whatever, horizontal or vertical, whose orientation can be set by Alice and Bob. And there's single photon detectors. And there's part of the instrument that counts coincidences. All right, so like I said, because the two photons have a common origin, they can be shown to be entangled. They're emitted in a cascade, and for a photon pair emitted in a cascade, the two polarization states are either plus plus or minus minus. So they both have plus helicity or they both have minus helicity. The coincidence between Alice and Bob's detection rates for anti-parallel photons, we're not going to derive this, but we'll take it as true. It's going to be equal to 1/2 cosine 2 phi, phi, where phi is the angle between the axes of the two polarizers. Okay. The original experiment that was designed by this guy named Kocher, the polarizers were oriented at 0 degrees and 90 degrees with respect to each other. And that means that the time correlation could be measured at, that A time correlation could be measured at 0, whereas no correlation was observed at an angle of 90. And Freedman and Clauser came along and they realized that that was sort of the weak point in the experimental design. The polarizer's inefficiency would make it prohibitively time-consuming to carry out the experiment and at a lot of different angles between the polarizers. And so Freedman and Clauser Instead, they chose what's called a pile of plates polarizer, which have much better efficiency. And so it took 2 years for Freedman and Clauser to rebuild this experiment so that it could be used to test the Bell inequality. So here's their setup. It looks really similar. So they have their calcium source, they have their 2 detectors, and in the experiment that they ran, the 2 detectors are 5 meters apart. So pretty far apart. And they wrote down, they kind of, so the CHSH inequality that we looked at, when you kind of rewrite it in terms of this experiment, this is what it looks like. It says that these guys, these are theta values. They're the coincidence rates at the angles between the polarizer axes of 22.5 degrees and 67.5 degrees. And R0 is the coincidence rate with the polarization removed. So you can rewrite the CHSH inequality as this. So it's the coincidence rates at 22.5 degrees divided by the no polarizer condition minus the coincidence rates at 67.5 degrees divided by no polarizer minus 1/4. That has to be less than or equal to 0. And when they did the measurement, they got something that was greater than 0. They measured 0.05. And that's a violation of the inequality. So when we look at, so they could do this measurement at lots of different angles. So here's the angles of the polarizers. Here's the ratio of the coincidence rates at angle normalized by the no polarizer condition. And so if we look at the values, that's 22.5, I think, and this one is 67.5. So those are the values, they measured those. Minus 1/4, they get 0.05. So this was a really exciting development. Like sort of all the theoretical results, Bell inequalities are derived, again, under these assumptions. And one of the assumptions that was really important to Bell was that the 2 observers, Alice and Bob, the 2 detectors, make random choices of what to measure independent of each other. So that's the local thing. So for that to be true, we have to make sure that Alice can't send a message to Bob about whether A1 or A2 is measured, that Bob receives before he decides to do his measurement. So in other words, we can't let Alice influence Bob's choices. And assuming that special relativity is real, then that locality condition amounts to making sure that that kind of a message would have to travel with a speed greater than the speed of light. So what Alan Aspect and came in and did was improve upon the Clauser-Freedman experiment to address this issue. So their detectors were only 5 meters apart, and it was, in theory, possible to communicate information that was received at one detector to the other before the second was measured. And the photon flight times, the difference in the photon flight times was about 20 nanoseconds. So if you could get the information there in 20 nanoseconds, that wouldn't be good in Bell's eyes. So Aspect proposed an experiment where an acousto-optical device would be used to switch the photons into two different branches of the apparatus on a time scale that's shorter than 20 nanoseconds. And that wasn't perfectly ideal either, because the distance between the polarizers was too small for truly random settings. And 15 years later, Zeilinger came in and he set up the experiment with observers separated by 400 meters so that there was no possibility of sending information between the two. And he did some other more minor technical improvements. And so this is what was awarded the Nobel Prize in 2022 in physics. So it was given to Aspect, Clauser, and Zeilinger for experimental demonstration of the violation of Bell inequalities, for experiments with entangled photons, and pioneering work in quantum information science. So this was like our first real example of this stuff being real. And it kind of is what kicked off the field that we're all so excited about now.